Hi, everybody. In today's lecture, I would like to talk about the concepts of heat and work and introduce the first law of thermodynamics. And I can't really do that without talking about this guy right here, James Prescott Joule. And that's because until the mid-1800s, the connection between thermodynamics and mechanics or the rest of physics, it really wasn't very clearly established. Now, James Joule, his family business was brewing beer, so he naturally had an interest in chemistry, and science for him was an interesting hobby. And because the family business was pretty successful, he had the leisure time to invest in his own experiments. And some of those most famous experiments involved demonstrating the link between the mechanical motion of objects and internal energy. So the way that he did that is sketched out here at right. What he did was he attached weights to ropes and pulleys, the weights here on the right next to this meter stick, okay? So as the weights fell due to gravity, they pulled on the rope, which turned the pulley, which turned the crank, and the crank is attached to some paddle wheels that are immersed inside a vat of water, okay? So the falling wheels caused the paddle wheels inside the water to turn. Now, because the container was insulated very carefully, what happened was that the water heated in response to the friction of the water rubbing on the paddle wheels, and that caused the temperature of the water to rise. James Joule was able to link the amount of energy that the weight lost as it was falling to the temperature change of the water inside of the insulated container. And in so doing, he established a direct connection between mechanical and thermal energy. And this hadn't been done before. And so we named the unit of energy, the SI unit of energy, the joule, in honor of him. And that's because these experiments led scientists to understand that conservation of energy was a universal law of nature. Before this, scientists had this idea called the caloric theory in thermodynamics. And this now obsolete theory hypothesized that there was a fluid called a caloric that flowed from hotter to colder bodies, and that caused changes in the temperature. And this is where we get the unit and name a calorie for the unit of energy. But we now know that energy is not transferred via some mysterious fluid, but instead via heat and work. So how do we define those quantities? Well, heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surroundings. When I envision heat, I always think about putting a pot of food or water on a burner on a stove, and that would be a perfect example of a transfer of energy by heat. Now, work in thermodynamics is defined as any other transfer of energy into or out of the system. This could be electrical, like running current through a wire, or it could be a push or a pull, like James Joule's paddle wheel. And then there's a lot of other forms of work, like the ones in pistons and engines that we'll talk about later. Now, transfer of energy into or out of a system, that means change. So we define what we call transfer variables. And the transfer variables are heat and work in this instance. But we've already discussed so-called state variables, and they describe the state of a system in a given instant. So some state variables that you're already familiar with include pressure, volume, temperature, number of molecules or number of moles, things like that. They describe the state of a system at a given point in time. Now, transfer variables, though, they're zero unless a process is occurring where energy is transferred across the boundary of the system. So transfer variables aren't associated with any given state of the system, only with changes in the state. And heat and work are transfer variables. So the first law of thermodynamics is a special case of the law of conservation of energy. And what it does, it describes the energy change, which I'll call delta U here, in the internal energy of a system. And remember, we define the internal energy of a system as the energy that you can't see with your naked eye, that's associated with the motion of the nanoscale and even picoscale components of a system, the motion of the atoms and molecules themselves. So the first law of thermodynamics states that the change in the internal energy of the system, delta U, is equal to Q minus W, or the heat minus the work. Now, when you express it this way, remember that all of these variables on the either side of plus and minus signs and equal signs have to have the same units. So all these quantities have the same units of measure of energy. The SI unit would be the joule, but sometimes we use units like the calorie or the food calorie, which is a kilocalorie, to express energy change too. So a calorie is 4.186 joules, and a food calorie is 4,186 joules. And you might also hear that called a kilocalorie. So when you state the first law of thermodynamics this way, delta U is equal to Q minus W, what it means here is that Q is the heat added to the system. So in other words, if you put a pot of water on the stove and you turned on the burner, then a positive Q would be the amount of energy that's transferred from the stove into the pot of water if you're viewing the pot of water as the system that's receiving that heat energy. Okay, so Q is the heat added to the system. Heat added to the system would cause the internal energy to increase if it's the only thing acting on the system. We call Q positive if heat is added, and Q is negative if heat is taken away from the system. So for example, if I take that same pot of water and put it in the refrigerator, then Q would be a negative number if you're talking about the heat taken away from the pot of water and dumped into the refrigerator, okay? Now also, let's talk about work. Stated in this way, Q is Q minus W. Work is the net work done by the system. So if work is done by the system, then the system loses energy. And if work is done on the system, then work is negative, and then Q minus W would be Q plus W, and the internal energy of the system would increase if there are no other things going on, right? Because the work would be a positive and tend to increase delta U. All right, so the sign conventions can be a little confusing here. Just remember, Q is positive if heat is added, right? And work is negative if work is done by the system. And then you're going to flip the sign to go the other way. Let me do an example here. If a system takes in 1,000 joules of heat, then that means that Q1 would be plus 1,000 joules. If the system then uses that heat energy to perform 300 joules of useful work, then that means that the system is doing the work. So work is done by the system. So that would mean that the work here is positive, say, for example, 300 joules. Then what might happen is that the system would then dump 700 joules of waste heat to its surroundings. It would lose some of that heat, right? So then Q2 would be minus 700 joules. There we go. Now you can see it easier. Q2 is minus 700 joules. So then in total, delta U would be equal to Q minus W, which would be 1,000 joules plus 1,000 joules minus plus 300 joules, and then minus 700 joules for the heat lost at the end. And then that net would be that there's no change in the internal energy of the system because it did take in some heat energy, but it used that heat energy to do useful work and then dumped the rest, and so there's no net change. Now, this is exactly what heat engines do, okay? They operate in a cycle, they take in energy from heat, and then they use some of that heat energy to do useful work, and then they dump the rest as waste heat to their surroundings. Okay, we're going to talk more about engines later, but I hope you got out of that some nice information about the first law of thermodynamics and the definitions of heat and work.